So this is a great introduction to some degree to my talk by Ian. This is going to be a bit of a review of some of the work I've been involved with regarding momentum balance and in the Arctic, so I focus in the Arctic, and atmosphere ice-ocean interaction. So with a little emphasis on something that's not exactly sea ice, which is the ocean just underneath, and starting looking at the role that this plays as well. So of course this is work with colleagues from SIPW, done at UCL, and I could list Danny Saltham and many people. So the motivations are quite simple. I put a little diagram showing sea ice, snow, and ocean underneath, and really we're interested in the coupling between these three layers, atmosphere, ice, and ocean, both in terms of heat exchange and momentum exchange. And the big picture motivation I didn't put, but it's some people have argued that we are performing the largest ever experiment by removing the sea ice cover in the Arctic. We allow the winds to stir the ocean up and maybe transform this relatively quiet ocean into something more dynamic, such as the Atlantic Ocean, for example. The typical currents under the sea ice are much lower than in the Atlantic. So that's one motivation. And understanding how the change of coupling between the atmosphere and the ocean affects, for example, redistribution of freshwater fluxes in the Arctic is very important in the context of thermohaline circulation changes. There's also a lot of implications in terms of understanding the sea ice extent dynamics, sea ice extent in the Antarctic, some work that Paul did that is known to be driven by winds, and the coupling with what drives the interannual variability of sea ice drift in the Antarctic, again, has to do with form drag and momentum coupling between the atmosphere and the ice. So that's kind of a big picture, but that was motivated by some work we started with Danny and Torge Martin and David Schroeder and others some years ago, 2 years ago. And what was quite striking, so this is exactly the parameterization that Ian introduced, so that's very handy. We have this form drag parameterization for the first time implemented in a sea ice model, in the size sea ice model developed by Elizabeth Hunke. And what we show here is that if we don't account for form drag parameterization, so the dependence on the roughness of the ice on the momentum transfer, then if we look at a typical standalone model over the last 30 years, there is an increase of the momentum stress to the ocean underneath. So this is the total, it's how much force the wind is exerting on the ocean underneath, the wind and the ice on the ocean underneath, over this area here. So it's in Newton per meter square, and it goes up on average over the last 30 years. If we put the form drag parameterization, we have this so-called smoothing effect. So instead of going up, it goes down. So that was a bit puzzling because it's quite a big change from going up, more momentum to the ocean, to going down. I have to add a caveat. It's a standalone model, and there are some limitations with that, but it was striking that this kind of parameterization can have a first-order impact even on the Pan-Arctic scale. So that's a paper that's now in JGR since last year. So the model develops, I can go quickly over that because it's this parameterization that Ian talked about. Ian focused mostly, okay, I don't seem to find the pointer. There's a big,
much more,
I saw it, pointer, good. So Ian focused on this little bit here. No, that's the so-called marginal ice zone. Okay, it's getting bigger as we've seen with Yevgeny, but it's the region that has low concentration. Actually, he didn't discuss too much the form drag parameterization associated to the roughness of the ice in the high concentration regions, which is also now parameterized in size. So these are the type of friction we're talking about. We will talk about form drag when it's friction over a blunt body and turbulence at the wake of this object. And then we talk about frictional drag when it's smoother objects, such as flat bits of level ice, or, I don't know, flat bits of level ice under the ice. So yeah, you have to bear in mind that what Ian showed was top atmospheric drag, but all this story also was parameterized for the ocean-ice interaction as well. So there are similar processes there. So this is now in a model. Just to highlight a bit more what we're talking about. When the wind is blowing on the sea ice, the ice is set into motion, and there are two contributions to the air-ocean interaction. The air-ice stress, so the direct, so there is wind pushing the ice, there is wind pushing the water, and there's actually ice pushing the water. So the total air stress, for example, would be some kind of weighted average between that and that. So that's also in the model. So just to highlight that this is now in the models, in the HADGEM model as well, it's now implemented, and in Paris, Wislau and Andrew Roberts have got it in their high-resolution model. So different groups have got a variation, at least, of this model. This is showing that this drag coefficient that Ian was looking at this region, for example, looking at drag coefficients here. This is a total drag coefficient, and there are different contributions due to ridges, due to the flow edges. So that would be dominating probably the effect in the marginalized zone that Ian showed. There is also a skin effect, just level ice. And then melt ponds can have a role to play, the edges of the melt ponds in the summer. And the total, what was quite new to see for us, was that it had, I mean, people have looked at that in the past. Bruno Tremblay already, I'm not going to say how many years ago, but he did some work parameterizing form drag based on ice thickness. So this is an idea that's been around for a while, but it's quite impressive to see that it can go up from 1 to 5, say, factor 5 difference spatially. And this, there's a lot of range of values also in the season. So in the winter, it will be almost half the value on average over the Arctic than in the summer values. So this is now nice and good. We did recently, we're doing the same in the Antarctic. And the nice thing with this parameterization is you don't need to tune it. In theory, if it captures the underlying mechanism by which form drag is controlled, then you plug it in the Antarctic and automatically it does the right thing. So that's the hope. So that's kind of on the modeling side. But I think the important thing, what I would say that at the end is we have a lot of model parameterizations these days, and we capture a lot of physical processes, but it's very important to constrain them as much as we can, and Ian's work was a good example of how you do that. But here I want to focus also on what kind of data I've been using more and more recently. So in the context of surface roughness, we've done some work with NASA, Operation Icebridge, to characterize the topography, the surface roughness of the ice. But we had the chance, and I have the chance to work at SIPW, and over the last 7 years we have this amazing tool that's CRISAT. It's been flying around 700 kilometers altitude and providing information on the surface, the ice thickness, but also you can gain information about the surface roughness. And also the currents. So I will show some of that highlights later. So the first paper we had 2 years ago with Alec Petty was a new product characterizing the topography at a high resolution. The aeroplanes give you a resolution of 1 meter, so it's an ATM, it's a laser spiraling and measuring very high resolution spatially of 1 meter, this topography. So you can, and it covers not what Ian looked at, but mostly the 100% concentration region where it's heavily ridged. So we did this algorithm, Alec in particular develops this nice algorithm, and we were able to detect these objects, the ridges, detect their average height and their typical distance. I'm not going to go into the details, but here is what is shown. Over the one particular year, I don't remember which, I think it's 2014, we have a typical height of these ridges over a length scale of the same distance as Ian, 10 kilometers typically. The typical distance between ridges, and from this, using the same Lübke's parameterization, you can infer a drag coefficient, not of the Svalbard, but now the other part of the Arctic, where there is 100% concentration. So it'd be interesting to see in the model what's the impact of heat fluxes and so on. Also for the parameterization, that of course here is A is 100%, so Ian's parameterization is not going to work here. So upscaling, other ideas to get information, pan-Arctic information about surface roughness. Again, this is a paper just come out in JGR, Earth surfaces. It's unbelievable how many JGR there are. Alec found this one. And they were kind enough to accept our paper. So the work we've done, and something Christian has done, also Christian has for a while, is we found a relationship between backscatter of the scatterometer, ASCAT, and our estimated drag coefficient from this approach with Icebridge. So there is some kind of functional, of course there's scatter, but we have this kind of functional relationship. That's very powerful, because if you believe in that functional relationship, you can expand and upscale to the entire Arctic, where you have some trust that this works. So we did that. And you see in the Arctic now you have this kind of maps of backscatter, but you can turn that into a map of neutral drag coefficient in places where this theory is valid. So for example, you see here you have this tongue of multi-year ice, and it will be rougher, and you would expect a larger drag coefficient. And we have now this kind of maps of drag coefficient. Actually, you can also plug in the parameterization that Ian did all over the marginalized zone, and then you turn that into a full map of neutral drag coefficient. So that's kind of what we showed there. I'm quite intrigued by doing the same in the Antarctic. There's some weird things happening in the marginalized zone. Some people have looked at that. I'm quite interested in this region, if that's an actual real roughness signature or if it's something else. I'm not 100% sure, but maybe we can discuss that. Okay, I think Jack Land is in the room, and Julian as well. We have some, Jack has done some great work. I think he's shown it, he has a poster, I think, on it, showing how roughness is important. I hope I've convinced you, but it's also important for something else, which is in predicting where the meltponds will appear. The meltponds appear in May, June, July, and they will form in depressions. So if you have rougher ice or smoother ice, it will change your likelihood to get meltponds or not. So that was quite, I wasn't aware of this paper, but it's been out. Jack Landy published this a few years ago, showing that if the predicted albedo, just from the roughness information in March, does an excellent job compared to the measured observed albedo. So with 2 or 3 months and possibly more lag time, you can predict where the albedo will be. Jack will explain better, but the point is that this could potentially bring the forecasting horizon of sea ice extent, because you've seen talks on meltponds. Meltponds are a great predictor of September sea ice extent. So if you can predict from meltponds, but if you can predict meltponds from roughness, then it's pretty powerful. So Jack has shown some of that potential. And this is some work we've done with cryosat, and this is to highlight the fact that with cryosat, again, this kind of calibration curves, sea surface roughness from ice bridge versus cryosat pickiness. Pickiness is a proxy for roughness. Let's not go into details. It's many other things, but there seems to be a link between a proxy from cryosat and some observation at a high resolution from ice bridge. So again, we investigate that, how we can get roughness maps from another satellite. The goal here is to start building up a long time period of roughness maps and informing the kind of models that Ian showed in the context of climate change and so on. Okay, so that was all about the surface. To go and get data here is harder. To go and, we've seen a talk by this morning about some measurement in the mixed layer, and you can do things, you can estimate drag coefficients, but it's much harder. You don't see that, you don't get access to that. So I'm going to talk about this because it's also crucial. The same process of form drag happens under the CS. So how are we going to get information on that? So one way to get information on that, and in my opinion is quite magic. You have a satellite at 700 kilometers altitude, and you're able, cryosat, but also NVSat, radar altimeters in general, you're able to measure the difference of height between the freeboard and the ocean. But you also measure the surface, sea surface height, the elevation of the ocean in between the sea ice. So you have the Arctic ice, but there are gaps everywhere, and you measure the sea surface height in these gaps, and you make a map of the sea surface topography, or elevation. So this was published by Tom Armitage, who did a PhD at UCL at SIPW, and he's built up a 14-year time series of sea surface height in the Arctic. That was then turned by us. He did a postdoc with me at UCL again, and it's quite easy to turn this surface topography into currents, geostrophic currents. This is basic fluid dynamics. And if you do that, we have a 14-year period of ocean surface currents. So this is a little animation, quite schematic, but the white parts are ice, so that's why I'm saying it's magic. You have the currents under the sea ice, so it's from a satellite. So, for me, it's quite striking. And these currents are informative in many ways, and in particular in how the coupling and the momentum transfer between the atmosphere, the ice, and the ocean will occur. Before, people were not aware of what these currents were. They assume a climatology, zero, or whatever they want to guess. Now we have an extra variable to constrain the problem, the momentum transfer. So that's, yeah. Okay, so I'm going to speed up a bit. So that's kind of textbook fluid dynamics, oceanography. You have two components in the momentum equation, the geostrophic currents, that's what we've measured. But you also have an Ekman component. We can deduce that. I'm not going to explain how, but Harry Harton also in the room is working currently on how to get the best estimate of this Ekman component in the current. But with both of these things, and Harry is actually implementing an inverse modeling approach to try and constrain these parameters in the Arctic. So I'm going to skip that because I'm short on time. And that. Just to say another motivation was the Antarctic. So this same idea is, of course, apply in the Antarctic. And we want to understand with colleagues from Knox in Southampton, and in particular our PhD student, Thiago, and also Jack, we want to understand the spin up and spin down of these gyres in the Antarctic Ocean and pole as well, and if a form drag has anything to say about that, and if knowing the geostrophic currents and the Ekman currents can help us better understand this. So just to give you a flavor. Just to finish, and it will be a bit of an introduction to Peter Williams-Stowe. In a sense, he's a kind of expert in ice-wave interaction. So we've done some work on wave-ice interaction. We will currently with Danny Feltham. So what's going on here? What's the form drag associated to waves? What can we say about that? Some early work we showed again with Chrysat that we are able to measure significant wave height in the open ocean now by fitting the return echoes from Chrysat 2. And Tom has done some earlier work on that, and we're working on providing this kind of maps of significant wave height. Again, as the ice, Yevgeny showed us that as the ice is retreating, significant wave height are likely to go up, and it's a key player in this momentum balance as well. So I'm just going to conclude with some obvious statements, but it's always good to remind ourselves that state-of-the-art sea ice models are now capturing a wide range of processes accurately. There are a lot of models and a lot of parameters. We need a systematic approach for validation calibration. We've seen a great example just before, but that's also an effort I'm trying to do. New efforts in data simulations, because this is the best way to inform model and observation, is to assimilate the observation in the model. And then against a wide range of observation and data that are often underused. An example is sea ice thickness. Often you hear in conferences, especially in America, we don't have a sea ice thickness product. This kind of strikes me a little bit because there's 7 years of great data from Chrysat. So that's just one example. And also in terms of operational forecasting centers, they don't assimilate yet sea ice thickness. Why? I'm not too sure. It's something to do. Could improve operational needs. That's something that there's a very strong push towards that. And also, of course, understand our modeling better, but also the observation better by comparing the models in a clever way with the observation. So I'm going to leave it here. And if there's 1 minute for questions. Yeah, thanks. We've got a little time for questions.
So I had a question right at the beginning. You said the form, you had each of your components of the drag, including the form drag, proportional to an ice area. I was a little surprised to see that bit. And is that implicitly assuming then that flows are roughly the same size, or that ridges are the same distance apart, or what's implicit in that?
There was an area weighting, ice area weighting slide. So it was, there's a direct stress on the open ocean, and then the stress of the ice on the ocean. So the simplest approach is to area weight the effect of the ice on the ocean and the effect of the air on the ocean. That is not correct. There are other approaches where you account for, because there is fetch of the ice part on the open ocean, and there are parameterizations that account for this kind of more sophisticated way of averaging. But and it's again work by Lucas, more recent work. So it'd be nice to implement that with maybe Ian if you're interested. I don't know where you are, but it's worth doing that work as well.
Okay. Yeah. Thank you very much.